Chapter 6: Carbon and some of its compounds. Carbon is the first element in group 4 of the periodic table. It is represented by the symbol C. With atomic number 6, it contains 6 protons and 6 electrons. Carbon is a well-known non-metallic chemical element present in all life forms. The element occurs in different forms in nature with a wide variety of physical properties and is abundantly found in the Earth's crust. Carbon exists in 2 forms, crystalline and amorphous. In crystalline solids, the constituent particles are arranged in a definite order. But in amorphous solids, the particles have no definite order of arrangement. Coal, coke, and charcoal are amorphous forms of carbon. Diamond, graphite, and fullerene are crystalline forms of carbon. Both these forms are called allotropes of carbon. Allotropes are forms of the same element which exhibit different physical properties, but with the same chemical composition. Let us now look at the crystalline forms of carbon. Diamond. Diamond is the hardest form of crystal carbon. In diamond, each carbon atom is bonded to 4 other carbon atoms by covalent bonds, forming a rigid 3-dimensional structure. Diamond's density is 3.5 grams per cubic centimeters. Here, no electrons are available as they are all involved in bonding. Because of the absence of free electrons, diamond is a bad conductor of electricity. Diamond has a high melting point of 400 Kelvin or more. Graphite. In graphite, each carbon atom is bonded to 3 other carbon atoms by covalent bonds, resulting in hexagonal rings which are arranged in layers above each other. One of the carbon-carbon bonds is a double bond, and thus the valency of carbon is satisfied. Since 1 electron of each carbon atom in graphite is free to move about, graphite is a good conductor of electricity. The layers are held together by weak van der Waals forces. Due to its structure, graphite is not as hard as diamond and is greasy. It's gray in color and opaque with metallic luster. Graphite's density varies from 2 to 2.5 grams per cubic centimeters and melts at 1800 Kelvin. Fullerene. Chemically, fullerenes are formed by chemical combinations of a large number of carbon atoms. The first one to be identified was C60. Fullerenes are often called buckyballs. The shape of fullerene resembles that of a soccer ball, with both 6-member and 5-member rings. There are 12 5-member rings and 26-member rings. In fullerene, all the carbon atoms are found to be equivalent and are connected by both single and double bonds. Chemical properties of carbon. Combustion. When carbon is heated, it glows red. A colorless gas is produced which reacts with calcium hydroxide to form a white precipitate. The red glow shows that the reaction produces heat. The white precipitate shows that the gas produced is carbon-4 oxide. All forms of carbon burn in oxygen to produce carbon-4 oxide. However, the temperature at which they burn varies from one allotrope to another. Reduction properties of carbon. In this experiment, we shall heat together a mixture of black carbon powder and black copper 2 oxide. The gas evolved is passed into a solution of calcium hydroxide or lime water. We notice the white precipitate of calcium carbonate formed as the gas is bubbled in the lime water. This means that the gas is carbon dioxide. As the black mixture is heated, the copper 2 oxide is reduced to reddish-brown copper by carbon, which is itself being oxidized to carbon 4 oxide. After the tube has been cooled, we can see the copper that has been formed at the bottom of the tube. When we pour the mixture at the end of the experiment, we can see that it is now red-brown due to the presence of copper. Similarly, carbon removes combined oxygen from zinc oxide, lead 2 oxide and iron 3 oxide. Carbon has the ability to remove combined oxygen from other metals. In these reactions, carbon is oxidized to carbon 4 oxide and the metal oxides are reduced to metals. In terms of competition for combined oxygen, carbon can be placed in the reactivity series of metal between aluminium and zinc. Thus, it reduces the oxides of all metals below it in the reactivity series. Therefore, carbon is a reducing agent. Oxidation is the addition of oxygen to a substance, while reduction is the removal of oxygen from a substance. The reducing property of carbon is used in the extraction of metals from their oxides. At temperatures above 1200 degrees Celsius, carbon reduces steam to hydrogen gas. Carbon in turn is oxidized to carbon 2 oxide. A mixture of the two gases is called water gas. Carbon 4 oxide. Carbon 4 oxide or carbon dioxide is the most stable oxide of carbon and is found as a colorless, odorless gas. It is made up of 3 atoms, 1 carbon and 2 oxygen atoms held together by covalent bonds, which means the electrons are shared between the atoms. Carbon 4 oxide makes up 0.39% of our atmosphere and it freezes at about -110 degrees Fahrenheit. Frozen carbon 4 oxide is called dry ice. Because it takes a lot of pressure to turn carbon 4 oxide into a liquid, when dry ice warms up, it turns directly from solid to a gas in what we call sublimation. Carbon 4 oxide is a rich source of the element carbon and the most important building block of life on Earth. Green plants use carbon 4 oxide during photosynthesis, turning the carbon into the sugar glucose during the process of fixation. Animals now use the glucose for energy. Carbon 4 oxide is used to extinguish fire and preservation of drinks often called carbonated drinks. Carbon 4 oxide from yeast and baking soda makes the dough to rise. In the laboratory, carbon 4 oxide is synthesized by reacting calcium carbonate with dilute hydrochloric acid. A few pieces of calcium carbonate are taken into a round-bottomed flask. Dilute hydrochloric acid is added and carbon 4 oxide is evolved steadily. The gas is collected in the jar by upward displacement of air because it is denser than the air itself. Carbon 4 oxide is a unique gas in that it has no liquid phase at normal atmospheric pressure. This is the solid form, dry ice. By sealing some dry ice in a balloon and using a warm bath of water, we see how it sublimes quickly to a gas. Carbon 4 oxide is about 1.5 times denser than air. It does not support combustion, but will react with burning metals such as magnesium. Notice the carbon deposit inside the gas jar. This purple solution is phenolphthalein in water, an indicator that turns colorless in acidic solution. Using dry ice again, we show that carbon 4 oxide in water forms an acidic solution of carbonic acid. Carbon 4 oxide will extinguish a burning splint, but the same will happen with ammonia. A more accurate test is to bubble carbon 4 oxide through lime water, which is an aqueous solution of calcium hydroxide, also called slaked lime. A white precipitate is formed due to the formation of insoluble calcium carbonate. Carbon 2 oxide. This is another oxide of carbon in which a carbon atom forms 3 covalent bonds with 1 oxygen atom. It is a molecular substance. The dot and cross diagram shows the 3 covalent bonds in a carbon 2 oxide molecule, one of which is a dative covalent bond. Carbon 2 oxide gas is colorless, odorless and slightly less dense than air. It has a low boiling point of -111 degrees Celsius. The low boiling point is because of the weak forces of attraction between the molecules. The gas is slightly soluble in water. The solution formed is neutral. Carbon 2 oxide is prepared by dehydrating methanoic acid, also called formic acid, with concentrated sulfuric acid. The gas is highly flammable and burns with a blue flame to form carbon 4 oxide. It is extremely poisonous to the cells. When inhaled, it seeps into the lungs, making way to the alveoli sacs, where it binds hemoglobin to form carboxyhemoglobin. This reduces the capacity of hemoglobin to bind oxygen, especially because hemoglobin has a higher affinity for carbon 2 oxide than oxygen, which suffocates the cells. In light exposure, one can feel headaches, sore eyes, and runny nose. Up to 15% exposure, you feel dizzy, confused, and achy. In extreme exposure, one becomes drowsy, lethargic, and slips into a coma, and this is fatal. Carbon 2 oxide readily removes combined oxygen from metals in low reactivity series, such as copper, lead, and iron. In turn, it is oxidized to carbon 4 oxide. The reducing property of carbon 2 oxide makes the gas useful in extraction of some metals from their oxides. Carbonates and hydrogen carbonates. Carbonates are salts of metal ions or ammonium ions with carbonate ions. The carbonate ions are indirectly obtained from carbonic acid, formed when carbon 4 oxide is dissolved in water. Carbonates occur naturally in rocks as limestone, malachite, and dolomite. Hydrogen carbonates are salts derived from carbonic acid formed by the partial displacement of hydrogen by a metal or ammonium radical. Hydrogen carbonates of sodium, potassium and ammonium exist as solids at room temperature, whereas those of calcium and magnesium only exist in solution. Hydrogen carbonates of other metals do not exist. Reactions of carbonates and hydrogen carbonates. 1. Reaction with dilute acids. We add 2 spatulas of zinc carbonate powder into a test tube. Then we add dilute sulfuric acid to the carbonate. A reaction is taking place and a gas produced. We need to know what gas this is. Warming speeds up the reaction. When bubbled through lime water, a white precipitate is formed, so the gas is carbon 4 oxide.
And so all carbonates react with dilute acids to form salts and carbon 4 oxide.
However, reactions between calcium carbonate or lead-2 carbonate doesn't proceed for long because calcium sulfate and lead-2 sulfate produced are insoluble and form a coat on the carbonate to prevent any further reaction. Note from these equations that the state symbols for the 2 sulfates is solid. Action of heat on carbonates and hydrogen carbonates. We will heat a sample of copper 2 carbonate. As we heat the copper 2 carbonate, it decomposes to give a characteristic black solid and a gas is evolved.
When the gas is bubbled through lime water, a white precipitate is formed, meaning it's carbon 4 oxide. The black solid is copper 2 oxide.
Again, when zinc carbonate is heated, it also decomposes. The white solid turns yellow and a gas is seen to be evolved. A drop of lime water is placed at the mouth of the test tube to test the gas produced. It turns cloudy, or more accurately, a white precipitate is formed.
So the gas is carbon 4 oxide.
On cooling, the yellow solid turns white, although at this point no further changes are taking place. This solid is zinc oxide.
And so, all carbonates of moderately reactive metals decompose on heating to form metal oxides and carbon 4 oxide. Carbonates of highly reactive metals like sodium and potassium are not affected by heat. On its part, when a sample of ammonium carbonate is heated, a choking gas is detected and a burning splint is put out. Ammonium carbonate decomposes on heating to form ammonia, carbon 4 oxide, and water. Hydrogen carbonates decompose on heating to produce a carbonate, carbon 4 oxide, and water.
sodium carbonate and sodium hydrogen carbonate. Sodium carbonate is used to produce glass, chemicals, soaps, papers, baking soda, and even in water treatment. Sodium carbonate can be obtained in two ways. 1. Extraction from trona, or 2. Preparation by the Solvay process. Extraction from trona. Trona occurs naturally in some regions of the world. But what is trona? Well, many million years ago, erupting volcanoes of the Great Basin regions deposited ash into huge lakes in various parts of the world. That sodium-rich ash mixed with the lake's carbon dioxide from decaying plant material and other minerals to form trona. Trona is a double salt containing sodium carbonate, sodium hydrogen carbonate, and water of crystallization. It is found in some lakes in Rift Valley. These lakes have only inlets but no outlets. In Kenya, trona is mined at Lake Magadi. Here, the placer mining method is used. This is mined using the dredging technique, using a special machine called the dredger. The dredger scoops trona from the surface of the lake. This trona is, however, mixed with mud. The scooped trona is fed into a crusher in the dredger and mixed with water or lake liquor. The mixture is pumped through a pipeline to the factory or transported by trucks. At the factory, the crushed trona is mixed with clean water in a washery where mud and small rocks are removed and the lake liquor pumped back into the lake. Wet trona is then centrifuged to remove water and purify it further. The dry crystals are then taken to a kiln or roaster where they are heated at about 300 degrees Celsius. This is then crushed into small sizes, sieved and packaged. On your screen is a flowchart of the processes in trona mining and processing. The Solvay process. In places where trona is not available, sodium carbonate and sodium hydrogen carbonate are manufactured by the Solvay process. The raw materials for this process are sodium chloride, calcium carbonate, coke, and ammonia. These raw materials are readily available and cheap. This is the plant system used in the Solvay process. Ammonia is dissolved in brine in the Solvay tower to produce ammoniacal brine. A lot of it is produced in this process. The amount of it produced is controlled by regulating the flow of brine into the Solvay tower. The ammoniacal brine is then pumped into the carbonator from the top where it trickles down the carbonator, while carbon 4 oxide from the kiln is pumped from the base. The carbonator has to be cooled regularly to reduce the amount of heat produced in it. The reactions that take place in the carbonator are as follows. Sodium hydrogen carbonate, being less soluble than ammonium chloride at low temperatures, forms crystals in the lower cooler part of the carbonator. Now, sodium hydrogen carbonate is separated from ammonium chloride by filtration. The sodium hydrogen carbonate is then dried and decomposed by heating at 300 degrees Celsius to produce sodium carbonate. The initial carbon 4 oxide used in this process is mainly from decomposed calcium carbonate and the burning of coke in the kiln. The ammonia used in this process is obtained from the Haber process. Calcium oxide produced in the limestone kiln is slaked or combined with water and mixed with the filtrate ammonium chloride to produce ammonia gas, water and calcium chloride. The Solvay process is one of the best examples of an efficient industrial process because pollution problems are considerably reduced. Carbon 4 oxide and ammonia gas produced are recycled to minimize the cost. The water produced is also recycled to minimize thermal effects on water source near the plant. The process does not involve large consumption of energy because the coke burnt in the kiln supplies the necessary heat in the process. The only byproduct in the process which is not recycled is calcium chloride, and it has a wide range of uses. The best site for the Solvay process plant should be close to a river or large source of water to cool down the carbonator.
And finally, the effects of carbon 4 oxide on the environment. Now, burning fossil fuels such as coal, oil and natural gas releases carbon 4 oxide into the atmosphere. Over a long period of time, using these fuels has increased the percentage of carbon 4 oxide in the atmosphere, causing carbon 4 oxide to act as a greenhouse gas. At the most basic level, the balance between the incoming sunlight and the outgoing heat determines the Earth's climate. Greenhouse gases act like a blanket and trap heat in the atmosphere. In the last 2 centuries, humans have increased the atmospheric carbon 4 oxide by more than 30% by burning fossil fuels. This is constantly leading to global warming and less dissolved gases in water.